Welcome to the session on forces in motion, connected particles. The objectives for this session are to understand and use Newton's third law and solve problems involving connected particles. Let's first begin by looking at the motion of more than one particle. In a system involving the motion of more than one particle, the particles can be considered separately or as a single particle if they are moving in the same straight line and connected. For example, they can be connected by an inextensible rod or string. Let's take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. So let's solve example 1a first. A car C of mass m kilograms tows a trailer T of mass 2m kilograms along a straight horizontal road. A light, inextensible rope connects the car and the trailer. The car exerts a driving force of 40,000 newtons, causing the car and trailer to accelerate at 8 meters per second squared. The car and the trailer experience resistance forces of size 3,000 newtons and 6,000 newtons. Find the mass of the car and also the mass of the trailer. So let's solve this. We're going to begin by drawing a sketch of the forces being exerted on the car and on the trailer. So let's begin with the car. Here's our car of mass m kilograms. The driving force is of 40,000 newtons. It's indicated going towards the right. The weight is indicated downwards, mg newtons, and the normal reaction force is of course being exerted upwards. And we're calling it Rc or R subscript C because this is acting on the car. And now for the trailer. It has mass 2m kilograms, so the force being exerted downwards is 2 mg newtons. The normal reaction force is R subscript T, and the tension in the light inextensible rope is T, and it's being exerted on the trailer and on the car. We also have, of course, the acceleration of both together at 8 meters per second squared, as shown in the diagram. And finally, for the rest of the sketch, the car and the trailer experience resistance forces of size 3,000 newtons and 6,000 newtons. So we have 3,000 newtons being exerted on the car and 6,000 newtons being exerted on the trailer. Let's now resolve the forces for the entire system. So we're considering the whole system as one unit. Of course, we have F equals ma, which is operating behind this. We have 4,000 minus 3,000 minus 6,000, which is the force. We have 2m plus m, which is the entire mass. And we have 8, which is the acceleration. And so rearranging gives us 31,000 equals 24m. And so m equals 1,291 2/3 kilograms. From this we have that 2m equals 2,583 1/3 kilograms. So the mass of the car is 1,291 2/3 kilograms, and the mass of the trailer is 2,583 1/3 kilograms. For part B, we are required to find the tension in the rope. Now let's just resolve the forces horizontally for the car. Again, we have F equals ma, so let's apply this to just the car. 4,000 minus 3,000 minus T gives us the net force, equals mass, which is the mass of the car, times 8, which is the acceleration of the car. And so tidying up gives us T equals 26,666 2/3 newtons. And finally, for part C, we are required to explain how the modelling assumptions regarding the rope affect our calculations. So let's solve this. The inextensible rope implies that the acceleration of the car and trailer is the same. The light rope implies that the tension is the same throughout the length of the rope, and the mass of the rope is negligible. This brings us to the end of this session. If you have understood its contents, you should be able to understand and use Newton's third law and solve problems involving connected particles. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.